delight to be in one of my favorite places with some of my favorite people, talking about one of my favorite topics these days, which is fast radio bursts. And just to cut to the punchline, we don't know what they are. Okay, so don't expect to find out what they are by the end of the talk, but I hope I will at least whet your appetites for this new astrophysical phenomenon. Let me describe to you what they are. So fast radio bursts, these are brief, and by brief I mean a few millisecond duration radio bursts that were discovered or first reported at least in 2007 by Lorimer et al. Using the Parkes radio telescope, which you could see here, at 1.4 gigahertz. And I'll just show you what this first event looked like. This is what we now fondly call the Lorimer burst. And start by looking at the inset here. Just you see a time series and then a burst that lasts a few milliseconds, and then it goes away, and there's no evidence for anything else. And I'll talk more about the dispersion of the radio waves in a second. Today we have, so since 2007, we've now detected about 30 of these events total. They are not microwave ovens. And I'll say a little bit more about that because I think it's actually kind of interesting the way that turned out. But in spite of, in the past decade, having detected only 30, we believe the sky rate, the all-sky rate, is about 1,000 per sky per day. So this is common, and the reason we've detected so few is just because conventional radio telescopes like Parkes have very small fields of view on the sky and limited on time, etc. We believe they are not only extragalactic, but probably cosmological, and I'll explain why. And the origin is presently unknown. So just to come back to the Lorimer burst, I said, so radio waves in the presence of free electrons, plasma, are dispersed. And that's what's going on here. So this is radio frequency on the y-axis and time on the x-axis. And what you can see is that the lower radio frequencies arrive later than high radio frequencies. And it's very well-known phenomenon studied ubiquitously for radio pulsars, and it's a 1 over frequency squared law, where the time delay between any two frequencies here, you could use the top and the bottom of the band, goes as the difference in frequency, 1 over the squares of the difference in frequencies, or the difference of the 1 over, you see what I'm saying, with a constant of proportionality, which we call the dispersion measure, which is the integrated electron density along the line of sight. And just notice it is an integral, no information about where those electrons are located. So you're summing over the column depth, wherever they're located. And dispersion measure is something that this cold plasma dispersion, you can read about it in Jackson or your favorite E&M textbook. And for radio pulsars, we've been using it for years to estimate distances in the galaxy to radio pulsars because their pulses are dispersed in the same way. And we have very nice models, actually, for the distribution of free electrons in the galaxy. This is a plot from Cortez and Lazio, which is the standard model used, although there are other newer ones, where here's the galactic center. Here is the Earth. You can see, crude spiral arms drawn in there. And this is a contour plot showing contours of constant free electron density, or rather constant dispersion measure in our dispersion measure units, which are parsecs per centimeter cubed, NEDL. And so what you could see is that for objects in the galaxy, and this is how we've traditionally used these kind of models, if you detect some pulsar in some direction and you measure some dispersion measure, say in this direction you measure dispersion measure 200, well, the model tells you roughly the distance. Similarly, if you have, so the model also predicts in any direction a maximum dispersion measure due to the galaxy. This is very important. So that in any one direction we can say, and this is now looking in the plane, but you can look at, it's 3D in any direction. You can predict fairly robustly, because these are calibrated using radio pulsars for which we have independent distance estimates. They're associated with supernova remnants. They have parallaxes. They're associated with some binary companion where you can measure the distance. In globular clusters, there's different ways. It's pretty well calibrated. So the most important thing is in any direction, we know pretty well, we think, what the maximum dispersion measure is due to our galaxy. And so for the Lorimer burst, which was the first FRB ever found, the burst dispersion measure was 375 in these crazy units, whereas in its direction, which detected by the Parkes telescope in Australia in the southern hemisphere, in the southern sky, the maximum due to our galaxy was 25. And this was shocking. We had never seen anything where the dispersion measure was greater than the maximum predicted. And not only that, way greater. This wasn't a little effect, it was huge. And this is what initially suggested, oh my goodness, this is not in the galaxy. Now, just to come back to the point about microwave ovens. Parkes was very good at finding these, and still is, mainly because they have a lot of on-sky time. It's a 64-meter dish, has a fairly large field of view compared to other radio telescopes, et cetera. But while they were finding FRBs, and this is back in 2014, 2015, they were also finding that some of the FRBs that they identified were a little different from the others. And by little different, they had these sort of strange sweeps that were kind of clumpy and not exactly frequency squared. And basically, there were other anomalies about them that I could tell you about, but the main one was the frequency sweeps weren't so clear. And you could really divide them just by this property into, regular ones, and they called them parrotons, the weird ones. But one thing that they noticed when they plotted the arrival times of these events as a function of local time, and here the light gray ones are the ones identified by their frequency sweeps as being anomalous, and the dark ones were the normal ones. They noticed that the anomalous ones peaked at lunchtime, which was suspicious. And they subsequently realized that it was due to an unshielded microwave oven on the Parkes site, but not only that the oven was, it wasn't that it was on, it was that somebody opened it prematurely. So that somebody was heating up their lunch, they checked it without turning it off first, and the telescope had to be oriented in azimuth roughly toward the kitchen. And they subsequently verified this. A PhD student opened it, recorded the time, over and over again, and this is unambiguous. And I think one thing that is really nice is, identifying the source of parrotons at Parkes. You can see, and this is monthly notices. I mean, they published this. I think it's beautiful. Subsequent tests revealed that parroton can be generated when a microwave oven door is opened prematurely and the telescope is the right angle. And, they published it, I think, kudos to them. But more importantly, and now you're going to ask me why microwave ovens do this. I don't know. And, none of them know. We've actually, over dinner, we said, why do microwave ovens do this? And we could sit and buy a bunch of microwave ovens. They all do it, and you could characterize all this. But we're astronomers. Time is short, 24 hours in the day. We're not going to study microwave ovens. As interesting as it's kind of curious. But anyway, the main point is that the distinct observational differences show that FRBs, the dark ones, the ones that matched independently, were identified as being, clearly cosmic, were distributed uniformly in time and were a cosmic phenomenon. And today, and I should really update this plot, but roughly they're distributed isotropically on the sky when you correct for the fact that most of them are found at Parkes, so in the southern hemisphere. And as I said, dispersion strongly indicates extragalactic, and moreover, as I'm going to say, it suggests cosmological distances. And if this is true, some of these things are really bright. They could make novel cosmological probes. So the Lorimer burst again. Why do we say cosmological distances? Well, conventional models for the intergalactic medium suggest at least out to reasonable redshift. I don't know exactly what the redshift limit would be, is that the dispersion measure from the IGM goes something like 1200 times Z. Sorry. And that would imply, if you take the Lorimer burst dispersion measure, subtract off the galactic component, Z of 3 for the Lorimer burst, 0.3 for the Lorimer burst. But, and if that would correspond to about a gigaparsec, which is cosmological, it's pretty far. But this is likely only an upper limit, and this is really important because the dispersion measures the integral. You don't know where it's located, so there could be some from a host galaxy. So the dispersion measure that we measure is the sum of that from the Milky Way plus the intergalactic medium plus whatever's in the host. And that's hard to know, especially if you don't know what the host is and you haven't identified a host galaxy. So if you, let's say, so you subtract off the Milky Way, which we believe we know, and then you divide the remainder equally in these terms. Yeah, it's arbitrary, might be right. Well, okay, that's about 500 megaparsecs. And that implies a radio energy of about 10 to the 40 ergs, or luminosity 10 to the 43 ergs. So I'm just setting the energy scale here for reasonable assumptions, although we don't know everything. And you could say, well, why don't you just go look for the host galaxy? Now that's the size of the Parkes beam. Okay, so there's a million, I don't know about a million, but there's a large number of galaxies in there. And you could say, well, what about a bigger radio telescope? So Arecibo, for example, and I'll come to Arecibo shortly, has a much smaller beam, but still nowhere near. This is something like 20, Parkes is 20 arc minutes. Arecibo is probably 3 arc minutes. Nowhere near enough to identify a galaxy. On the other hand, if you could identify one, observe one with the VLA, you'd be in business.
This is not the actual field of the actual
No. No, this is just... Yeah, in fact, the Lorimer burst was really near the Magellanic Cloud, the LMC. Okay, so first of all, a little bit on models. So currently, there's more models than there are events. I think the most constraining thing about them is their short duration, which, if the source size has to be less than c times the duration, that implies, something fairly compact. It's hard to escape that. The energy itself is not that constraining, so 10 to the luminosity, 10 to the 43 ergs per second is not, it's much less than, or 10 to the 40 ergs is much less than, gamma ray bursts. And by the way, you might ask, do you see any coincidences between FRBs and gamma ray bursts? And the answer is no, not so far. We checked this. Postdoc Sriharsh Tendulkar at McGill checked this, and we do not see any. Although I can't help but comment that I thought it was really interesting that the recent gravitational wave double neutron star merger at 45 megaparsecs had a really weak gamma ray burst. That's interesting. Now you might say, well, this is a cataclysmic event. There's easily enough energy in a cataclysmic event to account for 10 to the 43, or 10 to the 40 ergs. Supernovae, it's possible, but early on in a supernovae, you might expect the free opacity to be quite high. And so at radio wavelengths, would you be able to see this emissions, right away? That's actually kind of difficult if you run the numbers. It's a nice paper by Shri Kulkarni on this topic. What about compact object mergers? The rate is, we have 1,000 per sky per day for FRBs. That's much smaller than the rate that you infer. And you do it per galaxy or per cubic megaparsec, whatever. The rate is really low for that. So it's hard to imagine that's it. And the other point I think is important is that the radiation mechanism, it must be coherent. If you plug numbers in, the brightness temperature is very high, 10 to the 30-something Kelvin. But on the other hand, we've had this problem for years in radio pulsars. We know brightness temperatures in radio pulsars are very high. Suggestive there's some magnetic fields involved. But that's, I could talk a lot more about the various models that range from axion stars, cosmic stream cusps, objects falling into neutron stars, objects falling into black holes, alien light sails. Instead, as an observer, I'm going to stand back and just discuss finding them. How do we find FRBs? So you'll notice a lot of FRB people are radio pulsar people because we have the techniques, we have the familiarity with dispersion to correct for it. And we started to do single pulse searches some time ago because of rotating radio transients, RATs, which is a peculiar kind of pulsar that emits only occasional pulses. You don't detect them periodically. So to do this, you take systematic pointings of the sky with a large radio telescope, and for each pointing, you record fast-sampled and frequency channelized data. It's very important because if you're going to correct for a dispersion measure, which you don't know in advance, and you have to try many, many thousands of dispersion measures to find these things. It's a needle in a haystack kind of problem. So not only do you need fast sample data, but you want a wide bandwidth for sensitivity, and you want that bandwidth broken into many frequency channels. I mean, thousands of frequency channels. And you do that for some, this is basically what I'm conveying, is that it's a big data problem. Involves collecting petabytes of data. Radio frequency interference is a ubiquitous problem. We have students who do nothing but try and remove that. Not nothing. They do, part of what they do is try and remove that. Wouldn't be a very interesting deal. Anyway, then when you collect all these data, you de-disperse at thousands of trial dispersion measures. And then for each trial dispersion measure, you search the time series for peaks. That's basically how we do it. And it's a high-performance computer. You need a supercomputer if you're going to do this on a large scale. So two of the surveys that I've been involved in to look for fast radio bursts are the P-alpha survey using Arecibo, which is now operating again following the hurricane. We've been collecting data. They're not fully. It's not fully functional, but they are actually observing, which is great. And the Green Bank North Celestial Cap Survey using the Green Bank Telescope in West Virginia. Arecibo is a survey of the P-alpha survey is a survey of the galactic plane with the 7-beam receiver that is located in that little, suspended in that little dome. It's at a center frequency of 1.4 gigahertz, where all the FRBs until recently have been found. And I'll talk about Green Bank later. I might not have time to do anything but talk about the results from Green Bank. I thought I would show you just some data from our pipeline of what an event close to the detection threshold looks like. So this plot is showing you dispersion measure on this axis and time on this axis. And the dot size is proportional to the signal strength. So you see there's all sorts of garbage in the data, but right at the start of the observation, that black one, that triggers a little, our software, and we make what we call a waterfall plot. This is a radio frequency on the y-axis and time on the x-axis, zooming in on this object here. And yes, our baseline is terrible. There's a lot of interference in Arecibo data. But you see this clear peak, and you see that it's a broadband signal. This is here. It's now de-dispersed, so it's vertical. But as observed, the inset is showing you what it would look like pre-de-dispersion. So you see the sweep, and the white line is the predicted sweep. This just has different RFI mitigation. So this, and you might look at, that looks kind of crummy. But actually, this is a rat. So this one is in the galaxy, and we've seen it repeat many times. So this is real. And this is the detection threshold. Anyway, this is, you don't have to read this. This is an online FRB catalog. And the only thing I want to point out is a lot of the FRBs are parks. And then there's the one here found with Arecibo. And that's the one I want to talk about next. Right. The galactic plane overhead from Arecibo can only see in the declination range 0 to 40. So the galactic plane overhead is not the inner galaxy. It is the inner galaxy, but it's not toward the center. There we can see dispersion measures of 500, 600. But we tend to, for FRB searching, we're also doing the outer galaxy. And there the maximum DM from the galaxy is way lower. And the scattering, as I'll mention later, is not present at all. No.
I'm just wondering if the more you disperse, imagine the signal to noise goes down from the given observation.
Well, the truth is so the survey was set up to search for pulsars, so we're doing all the de-dispersion anyway for these surveys. So I want to concentrate on the one event thus far detected at Arecibo, which is FRB 121102. It was the first non-Parkes Arecibo, and I know they were probably delighted to have another telescope see one of these events. The dispersion measure is 558, which is 3 times the maximum due to the galaxy. So it's not the 15 or almost 20 times that the Lorimer burst was, but it's still, pretty out there. I guess some people wonder, is that high enough DM? Maybe your model's a little off. We'll get there shortly. But this is, you could see the DM sweep. The inset is the burst. This one had a weird spectrum. The spectral index, if you fit a spectral index, was +9, which in radio astronomy you don't see. That's unusual. And we assumed at the time that it was due to this event landing not at the center of the beam. Radio telescopes, the beam is diffraction limited, and it's highly chromatic. So if it, in fact, let me show you a plot. The next slide, one of the images on the next slide is huge. So here's Arecibo again. So this is the 7-beam receiver that's sitting under there. 7 independent positions on the sky. These are the beam patterns that you can see. And most importantly here, you can see if you threw in a flat spectral index signal, so equal intensity at all radio frequencies, depending where it landed, this is the outcome here is the spectral index you would measure. And you can see the scale here, and this is spectral index. The dark red is -10, and the bright and the dark gray is +10. Just because of the side lobes and that sort of thing with the receiver. And the point is that there is phase space in these gray zones to get a +9 spectral index, and that's what we assumed was going on. Just by luck, we landed somewhere in here. Now, you could say, well, the probability of that is so low. And yeah, but we just thought it's probably not intrinsic, and there you go. And we were wrong. The first thing that happened exciting about this source, and by the way, the Parkes FRBs, many of them they had looked at over and over again, never seen a repeat. The one we discovered with Arecibo repeats. So this was a shock. We initially detected about 10 more bursts. And just notice now, these are all de-dispersed pulses, so they're all vertical. And just notice the radical changes in the spectra. And this is now, we still don't quite know where it is in the beam, but it's always in the same position in the beam. These two events where here the spectrum is, strongly negative, and here the spectrum is strongly positive, were just, less than a minute apart. So it's very clear that whatever these crazy spectra are, they're intrinsic to the source. And not only that, the bursts come in clusters, so that we had actually observed this for many times before and not seen a repeat. And here is a plot that tries to depict, so once this happened, so I just realized I was here when Paul Schultz, the PhD student at McGill, discovered these repeat bursts. I was in Princeton. I was at that GR thing. And he sent out an email, and this is Canadian. He sent out an email with a subject line, minor point of interest about the FRB 121102. And I looked at that on my BlackBerry, and I was about to get up and speak, and I thought, oh, I'll read that after. And I went and I gave my talk about pulsars at that conference, and when I came back, there were 100 messages in that thread. Isn't that funny? Anyway, so this is a plot that's showing, so we've been observing it now with lots of different radio telescopes. We have Arecibo, GBT, Effelsberg, lots of different telescopes, and this is now MJD on the y-axis, and this is time on the x-axis, and the length of the line shows you the duration of any individual observation, the color showing the radio frequency, and the dots are showing you detections. And what you can see is there's long stretches where we don't see it at all. So all these observations of nothing, and then look at this burst storm here. So people ask me, oh, is it Poissonian? It's like, no. Clearly not Poissonian, and this is the inset here is zoomed in. You can see sometimes we get bursts every few seconds. Now, So there's lots of interesting repeater phenomenology, but let's just stand back a minute. Why only one repeater? Could there be different classes of FRBs? Some repeat, some not. Certainly in the GRB history, we know there are different types of GRBs, so it's not crazy. But, and obviously for the repeater, cataclysmic models are out the window. But is it a coincidence that of the 30 known, the only repeater is also the only Arecibo FRB? Like, that seems surprising. And many, in fact, I would say most of the repeat bursts would be too faint for Parks to see. Meaning, Parks can go staring at a repeater, but only see incredibly bright ones, so they have to look for too long. They don't have the sensitivity to detect repeat bursts for most of them. Maybe that's the explanation, but we don't really know. So I find that curious, but what could the repeater be? We don't know. So we don't know what regular FRBs are, and we also don't know what the repeater is. It smells a little bit like a rotation Parrot pulsar, and these are giant pulses. People are familiar that the crab pulsar, for example, has giant pulses. These are orders of magnitude higher luminosity, like something 6 to 8 orders of magnitude higher luminosity. You might think, oh, perhaps it's a magnetar. Magnetars are known to have giant flares, which are extremely bright in the soft gamma rays and X-rays, but they're not known to have giant radio flares. On the other hand, there are some aspects of known objects that vaguely resemble what we're seeing. The crab, its maximum luminosity is about 10 to the 35 ergs per second for the giant pulses. So still, like I said, nowhere near the luminosities of the repeating FRB, which are 10 to the 43. On the other hand, sort of curious, this is spectrum of one. This is now in microseconds, this scale. This is a few microseconds for a giant pulse from the crab. The frequency structure here, this is radio frequency. It has sort of this interesting structure, and it's not known what this is due to. But if you had a narrow band, you might see it falling or rising in the band. You might expect to see nanostructure in these pulses because you see that in the crab. So what about energetics? Radio pulsar energetics. The spin down, so the crab pulsar is, all of its emission is powered by loss of rotational kinetic energy due to magnetic braking in this rapidly rotating neutron star. And we can calculate what we call it the spin down luminosity is. Here the I is the moment of inertia, omega is the angular velocity. And so it goes like this expression here, where p dot is the rate of slowdown of a pulsar and p is its period. And for the crab pulsar, which is 33 milliseconds, and a p dot of this value, the e, the dot is missing, apologies. The dot is missing, 5 times 10 to the 38 ergs per second. So there's not enough energy in the crab to make FRB, but maybe if it goes as 1 over p cubed, so if you make the period a lot faster, a few milliseconds, you turn the p dot up. You can barely do this, but it implies a millisecond period magnetar. Yeah, so that's true. That's isotropic beaming. That's true. So that's true. Yeah. So pros of FRBs is magnetars. Magnetar giant flares have peaks that are a few milliseconds in X-rays. On the other hand, for galactic magnetars, we've seen 3 of these since 1979. That's about 0.1 per Milky Way per year. But FRBs would be about 10 to the minus 3 per galaxy per year if you do the numbers, taking the current rate as we know it. So that would imply we're sensitivity limited for FRBs, that there's a lot of FRBs that if we just had more sensitivity, we'd see them. Magnetars certainly have sufficient energy in the magnetic field. So here we're ignoring rotational energy, but the magnetic field implies pretty high energy stores. Even for a repeating FRB, well, there it depends on the activity lifetime of the FRB. If it is more than about 100 years, and yes, there's the beaming thing, then it gets a little dicey. Okay, so now once you have a repeating FRB, you can use an interferometer to try and localize it. And this is the VLA, and this is a very computationally demanding project because VLA doesn't normally give you images every few milliseconds, which is what you need, and it doesn't normally de-disperse. So this was a huge project to get the VLA able to produce fast sample data, frequency channelized, and have it be searched for bursts. And this is Casey Law and Sarah Burks-Bolar and Paul Demarest. People put huge amounts of effort into this, hoping to find new FRBs, but instead they could turn it to the Arecibo source. And they did this sort of fast imaging of the field, the 3 arc-minute field, in fall 2015 for 10 hours, no detection. Spring 2016, 40 hours, no detection. I'm sure the TAC at this point was ready to just kick us out. And then in fall 2016, we got a 40-hour slot, and in the first hour of a test observation, we detected a burst, and in that same observation, we detected like 10 bursts. And here's just this dispersion sweep in the VLA data. You know, it's unambiguous, very clear, at the same dispersion measure as all the repeat bursts. So if you're concerned, well, maybe it's some other burster in the 3 arc-minute field. No, it's the same dispersion measure. And by the way, all the repeat bursts are roughly at the same dispersion measure. There's a little bit of changes, but we're not sure it's intrinsic to the source. I could explain if you're interested. So once we had this, that was an arc-second position. And then you can go and, oh, by the way, the VLA observations detected a persistent source also. Sorry, I said 10. So 9 bursts in fall 2016. It was localized to sub-arc second. And coincident with the burster is a persistent source, about 200 microjanskis. And here you could see the flux of the persistent source. It is a little variable. The little triangles are when the burster was on. So it doesn't seem much like they talk to each other. In other words, the persistent source doesn't, it's coincident, and it shows the roughly 30% variability, but the variability doesn't seem correlated with the bursting. And then we could also go to the Gemini telescope. And, oh, by the way, here's the localization. These were the error regions Arecibo had seen the burster in, and that's the location of the object. And then we could go to the optical telescope. We detected a 25th magnitude counterpart, which turns out to be a low metallicity, high star formation rate galaxy at redshift 0.2. Which is a distance of about a gigaparsec. So sort of all the assumptions that we had made crudely were right for this source, which is very gratifying. It's a low mass, so now all the pulsar people have to learn all this galaxy stuff. So it turns out all these different types of galaxies. Who knew? And so this is a strange galaxy, low metallicity, as I say, high star formation rate. So I don't remember the number. You can look in Tyndall-Carr et al. So this got quite a bit of press. Even Fox News covered it. The New York Times. Radio burst traced to faraway galaxy, but colors probably ordinary physics. I really thought I'd like to bring a burster to Dennis Overby's home in the middle of the night and set it off and see how ordinary he finds that. Meanwhile, New York Post, scientists say radio signals in deep space could be aliens. Look at the news. Anyway, we could also look at it with the European VLBI network. Now that we have a good position, you can do VLBI and get even closer, even better position. And we detected 4 bursts in conjunction with Arecibo. We determined that the burst and the persistent source are separated by less than 40 parsecs, which suggests they're physically related, although not necessarily causally related. I mean, somehow maybe they're both in the same star cluster or something. And also it allows us to locate it within the central galaxy. The bursts are not coming from the center of the galaxy. Well, here's the dwarf galaxy. The center of the galaxy is shown, I hope you can see it with the blue ellipse. And there's better images in other wavebands where you could see the full galaxy. It's coming from a star formation knot. in the persistent, a star formation knot, both, and the persistent source is there and the bursting source is there. Okay. Oh, yeah, sorry, I did have this better. Okay, so here is the galaxy and the offset with the EVN position. So where do we stand? At least one FRB is definitely cosmological, but is it representative? What is the burst source? What is the persistent source? And it's very curious to me that, for example, superluminous supernovae are also in these low metallicity dwarf galaxies. Is that a coincidence? I think it's still a mystery why that is true, but now we have another weird source that's also in this type of galaxy. And I have 20 minutes left. So very quickly, coming back to searching for FRBs. So I talked about the P alpha one. Now, we also are searching for FRBs using the Green Bank telescope in West Virginia. The GBNCC, Green Bank North Celestial Cap survey, started out as a North Celestial Cap survey, but now it's a full GBT visible sky survey. And it's at a much lower frequency, at 350 megahertz. And we chose that frequency not for FRBs, but because we wanted to find millisecond pulsars for the nanograph for pulsar timing arrays. That's really the main goal of this. But you can also use the same data to search for FRBs, and that's what we're doing. Unfortunately, we haven't found any with Green Bank. And we have looked long enough that if the event rate were the same at 350 megahertz as it is at 1.4 gigahertz, we should have seen 10. Well, 10 plus or minus some number, but we were surprised, and this is a master's thesis work by McGill student Pragya Chawla, there she is, where she looked through tons of data and didn't find any. So this could constrain the spectral index of FRBs in as much as they have a well-defined spectral index. We've seen through the repeaters, they're wonky, they're all over the place. But on the other hand, there's other effects that could keep you from seeing at lower radio frequency. So for one thing, when you try and compare the event rate at one frequency to the other, yes, you have to assume some spectral index. That's the alpha. Also, you're comparing an event rate at one threshold, the Parkes telescope generally, because that's the one that's detected most events, with an event rate at a different telescope that has different sensitivity. You need some log n, log s function. You don't really know what that is. In fact, the population is consistent with a huge range, and so we adopted gammas here from 0.8 to 1.5, where 1.5 would be appropriate for a Euclidean universe. And then we performed Monte Carlo simulations, creating a population of FRBs that matched various alphas to see what alpha you would need to not have detected it at 350 megahertz. And here, the bottom line is here are the alphas for different gammas. So for different log n, log s relations, you get pretty different, actually not that different alphas. But I don't think these are that interesting. The main point is in doing that, you're assuming there's no scattering, and I'll explain what scattering is. And you're assuming there's no free absorption. So you detect them at L band at 1.4 gigahertz, and then something is happening that they're disappearing by the time you get to lower frequency. And by the way, LOFAR also hasn't seen any FRBs. And so scattering is an effect that we're familiar with. We see it in galactic radio pulsars, where inhomogeneities in the electron density cause pulses to be broadened. Basically, rays that would have gone elsewhere get scattered back into your line of sight, and so you get the pulse convolved with an exponential, with an exponential tail, very frequency dependent. So at high frequencies, it's almost not an effect. At low frequencies, the tail grows. It grows as frequency to the fourth power. And so really, you have to take that into account. And we did simulations that take this into account, et cetera, et cetera. The bottom line, scattering could easily kill you. It could be the reason you don't see them at 350 megahertz. Independent, you could set different limits on the intrinsic spectral index, which are very different if you don't assume scattering. And then free absorption, we didn't even touch. Okay, so the FRB rate versus radio frequency, many are observed at 1.4 gigahertz. There are now several observed at 800 megahertz. One at Green Bank, several with the Utmost telescope. That's the refurbished Molonglo telescope in Australia that's being run by Matthew Bales' team. So 800 megahertz, we've seen now a few. GBNCC at 350 megahertz, none is observed. So something happens between L-band or 800 megahertz and 350 megahertz. Wouldn't it be nice to have a really sensitive FRB search in the 400 to 800 megahertz range, because that would tell you why they're disappearing. And that's what I'm going to talk about next. So CHIME is the Canadian Hydrogen Intensity Mapping Experiment, which is a radio telescope that is built. It's completed in Penticton, British Columbia. You could see it pictured here. It has an unusual geometry. So it's not a dish like other radio telescopes. It consists of 4 cylinders. Each one is 20 meters wide by 100 meters long. So the area is, I hate to do this, but something like 5 to 6 hockey arenas. And you're Canadian, you have to make some reference to hockey. There's no moving parts. This is a transit telescope. Along the axis of each of these, and so as a dish focuses to a point, or at least a circle, a cylinder focuses to a line. And along that line, along the axis of each cylinder, are 256 feeds per cylinder, dual polarization feeds, so we have a total of 2,048 inputs. And I should have said these cylinders are oriented north-south. North-south, so the sky drifts overhead, and the frequency range is 400 to 800 megahertz. And by the way, this frequency range was not chosen because of the reason that I've motivated it. It was chosen for totally different reasons. This telescope was conceived of and designed for a totally different project, and that's why it's called Canadian Hydrogen Intensity Mapping Experiment. This was to map highly redshifted hydrogen to study baryon acoustic oscillations and dark energy. And I am not involved in that project. Came in much later, suggesting that the telescope signal could be split and we could find FRBs with the same instrument at the same time that the cosmology experiment is going on. Now, what's remarkable, the reason this is such a fantastic transient detector is that the field of view in east-west, it's a couple degrees, north-south, it's about 120 degrees. And so you have a 250 something, 220, 250 square degree field of view that is many orders of magnitude greater than any conventional radio telescope. Parks's 20 arc minute field of view. The beam size is about somewhere between a half a degree and 20 arc minutes, although we will be able to localize sources, if they're bright, to about 1 arc minute, the brightest ones. Still, that's not enough to localize them, if you're wondering. And this is fully funded. You can see the web page here. And it's a collaboration, the CHIME Fast Radio Burst team. This is not the cosmology team, that's different. Although there's many overlap, many people who are involved in both. And there you can see all the names. And I guess the one thing, don't read all the names, but I think it's really important to recognize that this pretty large telescope is being built by postdocs, students, a few programmers, but it's really very much a university. So the National Research Council of Canada has given the land, and there's some people from there who are working on it. Tom Landecker in particular has been really helpful. But this is really a university project, and the students and postdocs have been absolutely phenomenal. And just to set the scale, there we are standing in the axis of one of the cylinders, so it's a very large telescope. And just just to explain exactly, more or less how this works, if you had just one of these feeds along one cylinder, the cylinder focuses to the line, so this would be your beam on the sky, roughly speaking. And then if you populate it with a lot of feeds, then you can create an FFT telescope in the north-south direction. I guess there's people in the audience who are quite familiar with this idea. We have 256, so this is not, and we're going to make them a little bit closer. And then if you have all populated, then you have the full field of view, but you can search each spot independently. Each spot is an independent position on the sky. So it's like having 1,024 GBTs, each of which you're getting time series from. And here we're written about in Nature. It's a half-pipe array to map the teen universe. But of course, that's not all. It can also detect FRBs. The signals from all of the antennas go into, it's a massive correlator. It's the largest, by far largest correlator in the world. The signals go, it's an FX correlator, for those of you who are familiar with this. The F term, which is FPGA driven, manages the frequencies, divides the band into frequencies. That's located in these two huts that are literally sitting under these two cylinders and under these two cylinders. And by the way, the input data rate is 13 terabits per second. It's comparable to the global cellular network. And then the F engine spits it out into the X engine portion of the correlator, which is GPU based and does the spatial transform. And then the signal actually goes and is now split into the radio burst, so FRB search engine, the map maker for intensity, for hydrogen intensity, and we're also doing pulsar timing, and that's a whole other talk. We're doing lots of pulsars with things, very exciting. Running out of time, so I will skip the pipeline diagram, but I'm very excited to announce that we have first light. So this is just a week and a half old, very excited. We have detected pulsars with the system. So this represents so much work by so many hardworking, motivated, excited students and postdocs who stayed up all night to get this stuff to work, debugging, hacking. What you're seeing here is, this is time. So these plots are really new. They're not that well explained, but this is time. This is basically 36 hours of observations, but with an incoherent beam. So we don't have the phases between the antennas correctly. We're just summing up the intensities of all the 1,024 antennas and searching that sum. So this is nowhere near the sensitivity we will be able to achieve. Yet we can see pulsars. This is now event rate versus time. And this peak here is pulsar 0329 plus 54, one of the brightest radio pulsars in the sky. And in fact, this is now a DM transform. So without getting into too many details, this is the x-axis here is time, where the separation of these little events here. So down here is where the pulsar is. And the y-axis is dispersion measure. So obviously, it's a really nearby source. This is a radio pulsar in our galaxy, so it's very low in DM. This goes up to a few thousand. We're actually searching way out there. And the separation of these pulses is the period of pulsar 0329, something, I forget, 0.7 seconds or something. And you can see it transited. This is now the signal strength, the individual events as a function of time. This is the transit. So, we're super excited, but there's still a lot of work to be done. We're still commissioning, still debugging. We have to phase the whole thing up. It's a lot of work. But once all that is done, CHIME should be a really great FRB detector. 220 square degree field of view, 400 wide bandwidth, large collecting area. This is now predictions for bursts per hour on the x-axis, and it's observing frequency on the y-axis. The rates are basically set at L-band by Parks, and you now have to assume different things about the spectral index, which we don't know, or about the scattering, which we don't really know. But here is for a gamma log n log s of exponent 1.5, and for ranges of alpha that correspond to our best, from the Green Bank survey and Pragya's paper, we estimate the plausible ranges of alpha for reasonable assumptions about scattering. And so that's why the box for CHIME is really quite large, because there's a large error range given what we don't know about it. But the middle of the error range corresponds to about a burst per hour for CHIME. So there's been 30 detected since 2017, but when we finally are in production mode, we should have a couple dozen per day. And the rate may well vary over the band. There's a very wide band, and as we say, they disappear, but we'll see. And so CHIME FRB is my second to last slide. What would you want to solve this problem? If you don't know what FRBs are, how are you going to solve it? You might want, number one, statistics. You might want thousands of events to get the correct event rate, the flux distribution, log n, log s properly, the angular distribution on the sky, maybe they're not fully isotropic, I don't know, the DM distribution, the scattering distribution, correlations between these two, all sorts of things. That's what CHIME can deliver. Since the sky comes back every day, every position on the sky comes back every day, we can detect lots of repeaters and rule out repetition, so that is good. We plan to do all these detections in real time. That is what our pipeline is designed to do. The latency is at most a couple seconds if it works, if it works properly. There's a lot of great students, postdocs back at McGill and UBC in Toronto working on these things. Arc-second localizations, that it can't do. It cannot do it. But if there's multi-wavelength counterparts and we can detect them quickly enough, that might provide the localization. Or an idea we're thinking about right now is making little mini CHIME outriggers with the same frequency range across the Canadian landscape. And that you could do VLBI possibly in real time. That's something we're thinking about. In principle, we can get out linear polarization information as well, but that requires a little extra work that we haven't done. So conclusions. FRBs are here to stay. The origin remains unknown. Perhaps all repeat, but we don't really know. The first localization is accomplished. The cosmological distance is confirmed. The GBNCC non-detection suggests 400 to 800 is a good range, and CHIME will be a great FRB machine. And I want to thank a lot of amazing students. I keep repeating this, the fantastic team, very motivated, our funding agencies, and I will leave you with a drone flyby of CHIME. Thank you very much.